The topic of my presentation is AVM video codec architecture and performance. First, let's speak about the AU Media video codec working group. I'm a co-chair of this group together with Andrey. The group develops video codec related specifications, and so far it developed the AV1 specification, then the AVIF image format, which is basically a container for the AV1 intra. And recently we also published the AFGS1 specification, which is the film grain from AV1 that can be used with other video codecs using the ITU-T35 SCI messages. The ongoing work of the group is video compression beyond AV1, and that's called the AU Media video model. So what's the AU Media video model? That's basically the software code base that is based on LibOEM, the AV1 reference software. But AV1 reference software, it had like a lot of production-like features and a lot of optimization. So the AVM software was branched of this of LibOEM. It's currently hosted in GitLab, and the software has been cleaned up. Some production code was removed, and for example, the fixed QP mode was also implemented. That is usually used in the development of video codecs. So the codec working group operates in a way that if there is a new tool submission, it should contain the code, a document, and the test results according to the common test conditions. And then the group performs the review. If there is a consensus, then the tool is accepted in this code base. So what are the AVM features? The architecture is a hybrid block-based, so the same architecture that has been fueling the development of video codecs for quite a while now. This code base currently has over 200 new experiments, and experiment doesn't need to be necessarily a new coding tools. Sometimes it's a new coding tool, and sometimes it's a change of an existing tool. So, and that's why the gains per experiment vary significantly. Some of them can bring, let's say, more than 2% bit rate reduction, and some of them are quite small. So you can think about AVM as a toolbox, and perhaps not every tool that exists in this toolbox will end up in the future video codec specification. Currently, it's mostly the traditional video codec tools. There are some data-driven tools, basically when you train your tool based on some videos. But really, like, there are some machine learning tools that are being investigated, but they haven't been. There hasn't been an agreement to adopt them to the code base yet. Here you can see some examples of the coding tools that people worked on, so split into different groups, so like partitioning, inter-prediction. You can see that, for example, inter-prediction is a very popular field. Like some tools bring pretty big gains, like TAP, for example, and the transforms is another area where people did work, including the data-driven transforms, and also the quantization has changed compared to AV1. Extensive work on the in-loop filters, including the cross-component loop filters and improvements to the existing loop filters, and some work has been done on the coefficient coding and the entropy coding as well, even though like the base entropy coding stays the same as in AV1. So next I'm going to speak about the extended recursive partitioning, since that's probably one of the blocks that you start kind of implementing the codec width. So here you can see the partition, available partitions in AV1. So in AVM, basically, a number of partitions have been removed, so you don't have those anymore, and some more partitions have been added instead. So, like you can see, for example, H partitions and some asymmetric partitions. And in general, this partitioning scheme is more flexible and brings gains. Currently, the super block that is being subdivided by this by partitioning, it can be up to 256 by 256 samples, but the processing can still be done on 64 by 64 blocks, so to enable the hardware friendly processing. Also, some long blocks are allowed, like for example 64 by 4. The quantization, as I mentioned, changed significantly. AV1 had some bespoke quantization tables, separate for AC and DC coefficients and even different bit depths. The encoder QP parameter was from 0 to 63, but internally the parameter could vary. This parameter could vary between 0 to 255, and that was the so-called Q index. For AVM, there is an exponential dependency on the Q step on the Q index, so you can express it using a formula. And the Q step doubles every 24 Q index values, so there is more, a finer granularity than, for example, in the MPEG family of standards. Also, there is a wider range of quantization steps compared to AV1, so now you can go basically to lower bitrate using coarser quantization. Also, a TCQ, a trellis-coded quantization, was added, which is a coding tool that has been used in some standards since JPEG 2000. The in-loop filters, as I mentioned, there has been a lot of work in the in-loop filtering, including the loop restoration, Wiener filters, cross-component filters, and so on. I'm going to speak about deblocking just because I have proposed it. Basically, in AV1 there was several deblocking filters for different block sizes, for different filtering length. They all were replaced with one generalized filter that preserves details. So you can see, for example, that the blue line is basically shows you a step, like basically a block artifact, and after the deblocking is applied, the red line shows how it would look like, and you can see that there is some structure at the sides of the block boundary, which is kept there, and these low-pass filtering operations are left to other loop filters, because nowadays in NVIDIA codecs we have a lot of loop filters, so you don't need to immediately low-pass starting with the deblocking. Next, I'm going to speak about the performance of AVM. The performance is evaluated based on the common test conditions. It has 4 different configurations, all intra. Every frame is encoded separately from other frames. Random access configuration, basically hierarchical by prediction with closed GOP. The low delay configuration, so one intra frame or key frame followed by the encoded frames without reordering, and the adaptive streaming, which is basically it's similar to the random access, but you build the convex hull based for the 4K sequences based on the regional sequences and the downsampled ones. So the CTC for AVM have like a number of test video sequences, 69 mandatory sequences, and 23 optional, and number of images. It uses a one-passed fixed frame QP structure, closed GOP, and the sub-GOP size is 16 frames. So 6 base QPs are used, and the bit rates is calculated according for PSNR, SIM, VMAF, and a number of other metrics. And of course, we also report the encoding and decoding time. So the AVM results basically are rather new ones. The recent anchor was released in January 30th this year, and the comparison is done for this anchor version 9 versus so what we call the AV1 alternative anchor version 4, which is basically AV1 plus the AVM quantizer, because that allows you to use a similar frame QP offsets and the similar frame structure, prediction structure as in AVM, and also we port the encoder optimizations that we adopt to AVM. We also port them into this anchor. So you can see that the results vary depending on the configuration. Typically, you use random access to see the improvements over the previous generation of the standards, and the YUV PSNR is over 27% compared to AV1. And if you look at the VMAF VD rate, it's over 30%, which can indicate that we are doing better subjectively for the visual numbers. You can notice that the encoder and decoder runtimes are pretty high, but I would like to bring to your attention is that basically the anchor here is very well optimized. That's basically the LibOEM, which is nearly kind of production, maybe not quite production, but still a pretty fast encoder and the decoder, and the AVM is a mixture of like optimized and not optimized research code. So in general, the hardware companies are saying that we are well within the budget for the next generation decoder. So I think we are doing fine on the complexity side. Also, if you look at the random access results per different class of sequences, and the classes here are different resolutions, and B1 is basically the synthetic content, including animation, and B2 is screen content coding, which has somewhat more gains. But if you look for other classes, you can see that the gains are pretty uniform across the resolution, maybe with a difference of a couple of % bit rate. So some Netflix contributions to AVM development, test sequences, support of VMAF and other quality metrics, generalized deblocking filter, intra-direction interpolation filter, improved transforms, coefficient coding. Also, we've done some work on debanding, even though it's still under the consideration, and then the trellis-coded quantization, which is joint with Google. So if you would like to contribute to AVM, basically you first should decide if it's just a patch or something that would change the sort of the codec, and if it's just a patch, you can sign the CLA and just contribute to the code base. If it's a tool, your organization need to join the codec working group, and then you can start contributing tools and patches and participate in the meetings. If you are a university, so one approach is to join the AVMedia. Some universities are members, and we also have some pretty inexpensive tiers of membership for small companies and universities. Otherwise, you can find an industry partner who is a member, and then work on a joint project, and then your partner company presents it. There are also other working groups that I didn't speak about in AVMedia, which is storage and transport formats, software implementation, volumetric visual media, and audio codecs. So the AVMedia is basically nowadays doing more than just video codecs. And yeah, if you want to participate in some working group, you can choose which one you participate, and you completely ignore other that you don't want to participate in. So thank you, and yeah, I'm ready to answer questions.
Thank you, Andrey. So before we take question, one burning question. SVT-AV1, is it part of the software group?
Software implementation.
Okay. So what you do is completely different from SVT-AV1?
Yeah, it's a different, basically they use a different code base. And
yes.
Actually,
yes.
Yeah. And
different code base. So we have basically libaom, SVT-AV1, and now we have AEM as a tool.
AVM, yeah.
Okay, for those who are not speaking AOM fluently, I think it's good to know. Any questions? No one has questions? Okay, Andrey, maybe at the break in a few minutes. Thank you very much.
Thank you.